Welcome back everyone to 11.8 Power Series. In this video I have 4 more examples for you just to give you a taste of different things that can happen with our Power Series. So let's get to it with an example. So we want to find the radius and interval of convergence for the following Power Series. And this one's decently complicated. But the big thing here that I want to point out is that we're no longer dealing with an open interval, we're actually dealing with just the interval of convergence. So I'll show you how that matters here in just a bit. So as usual, with our power series, we're going to apply the ratio test, right? So I'm writing down my limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. So I'm just going to go ahead and multiply by the reciprocal. So that's going to be my n squared plus 1 divided by n times x plus 3 to the n. And again, we see some things cancel. All right, there's one more x plus 3 in the numerator than there is in the denominator, and the other stuff doesn't cancel as nicely. So this is going to be the limit as n goes to infinity. And now we can see, well, this x plus 3 is actually constant. It doesn't have any n's in it whatsoever. So let me pull this off to the side here. And then times the absolute value of, and we're going to have our n plus 1 divided by n. I'll group that stuff together. And then our n squared plus 1 over, and let's go ahead and expand this out. Let's see, this would be n squared plus 2n plus 1 plus 1, so that's going to be plus 2. And now we can see that this polynomial, my n squared plus 1 over n squared plus 2n plus 2, well, this should go to 1. And we can use L'Hopital's, or we can use Calc 1. So either way, you can see that this goes to 1. Right? So let's go ahead and just write it. This absolute value of x plus 3 should be, well, again, ratio test says we would want this to be less than 1 if we want it to converge. So, okay, let's go ahead and notice a few things here. Right, so it converges if x minus a is less than r. So here my a was -3. So you can see that this actually is my x minus a, x minus -3 is less than r. So this is telling me that my radius of convergence is r, right? So I had 2 goals. Find the radius. So I probably should say radius of convergence, but it says radius and interval of convergence, and then find the interval. Okay. So if I break this up using the theorem that we learned last time, we can see that I can find the interval that x must be between -4 and -2. And this tells me the open interval of convergence. But it turns out the ratio test falls a little short. It doesn't tell me what happens when x and a are exactly distance r apart. So in this case, when they're exactly distance 1 apart, what happens? So when you're trying to figure out the interval of convergence, you need to test the endpoints. So I'm going to test x equals -4, and I'm going to need to test x equals -2. So if I plug in -4 for x, so I'm going to have the sum from n equals 0 to infinity of n times, when I plug in -4, this gives me -1 to the n over, still my n squared plus 1. So the claim is we know that this actually converges by the alternating series test. Right? We're trying to figure out the interval of convergence, and the question right now is, does -4 make this converge or not? Right? Okay, if I plug in -4, would this converge? The answer is yes. And again, it's by the alternating series test. Because the limit heads towards 0, right? The limit of the terms, and it's decreasing, so perfect. How about for x equals -2? And actually, let me pause for a second. So I need to change my interval of convergence, right? So I need to now use brackets around -4 because that is one of the values of x that makes the series converge. Okay, how about for -2? Should I change that to a brackets or not, right? Does this make the series converge? Okay, well, when I plug in -2 for x, this gives me the sum of n over n squared plus 1. And the claim is that this actually diverges. And there's a couple ways you can show this, but I think the easiest is the limit comparison test. So again, this is positive. It's decreasing. Great. really the limit comparison test, we need something to compare it to, and the right thing to compare it to would be 1 over n. We know 1 over n, that this series would diverge because of the p-series test. So at x equals -2, the series diverges. So the interval of convergence is -4 and including -4 to -2, but not including -2, right? There it diverges. So this is important because WebWork doesn't have you do the interval of convergence so much. It's more interested in the open interval of convergence. And yet I've seen on quizzes and exams, instructors ask for just the interval of convergence. So if that comes up, you're going to need to be ready to show this sort of work. You're going to need to test the endpoints. So let's go ahead and get some more practice here. Again, we're trying to find the radius and interval of convergence, different series. So this is a sum from n equals 1 to infinity of x to the n times the natural log of n. So again, as usual, I'm going to start with the ratio test. The ratio test is going to help me find the open interval of convergence. As we can see here, there's one more x in the numerator than there is in the denominator. So this is going to be, and I can go ahead and factor out this absolute value of x, right, because this is constant with respect to n. So I'm looking for the limit as n goes to infinity of the absolute value of the natural log of n plus 1 divided by the natural log of n. And so how do I figure this out, right? So I need L'Hopital's rule. So L'Hopital's rule, right, this isn't an indeterminate of form infinity over infinity. So if I take the derivative of the top, I get 1 over n plus 1. If I take the derivative of the bottom, I get 1 over n. So this is the same thing as the limit as n goes to infinity of n over n plus 1, right? Instead of dividing by a fraction, I can multiply by the reciprocal. So that's how I get that. So now this heads towards 1. That's, again, we could use L'Hopital's rule again, or you could remember horizontal asymptotes for Math 132. And so we get the absolute value of x must be less than 1. Well, when does that happen? Well, first of all, let's talk about the radius, right? The radius is going to be 1 in this case. We can see that our a was 0. So the thing on the other side, right, x minus a, the absolute value of this must be less than r. So r is 1, perfect. And if I expand this out into an interval, right, using that theorem that I gave you, this is going to be the interval from -1 to 1. But I need to test the endpoints, right? Because it's not asking for the open interval convergence, it's just asking for the interval of convergence. So maybe my first value I'll plug in is -1. Let's see, does this converge or not? Well, if I plug in -1 for x, I get the sum from n equals 1 to infinity of -1 to the n times the natural log of n. Okay, so does this converge or not? Well, the claim is that we know it has to diverge. Why does it diverge? Well, its claim is that the limit of just the sequence itself doesn't converge. So by the nth term test, remember the good old nth term test from back in the day, we know that this diverges. And it turns out, likewise, if I was to plug in just 1, this would be the sum of the natural log of n. And this gets bigger and bigger and bigger. In fact, it heads towards infinity, right? The natural log of n gets bigger and bigger. So again, this is going to diverge by the nth term test. Remember the nth term test, the only way that a series can converge is if the sequence of its terms approaches 0. So when they don't approach 0, in the first case, they didn't converge to anything. In the second case, it converged to infinity. Well, we have no hope, right? So it has to diverge. So in this case, we don't add in either of the endpoints. It just stays from -1 to 1. So sometimes that happens. All right, another example, different series. I have the sum from n equals 0 to infinity of n factorial times x to the n. Let's figure out what happens here. Again, we're trying to figure out the radius and interval of convergence. Again, I start with the ratio test, as usual. Get a little bit of good cancellation going on here. I have one more x in the numerator than I do in the denominator. And the factorials, right? The factorials should cancel a little bit. So n plus 1 factorial, remember this is the same thing as n plus 1 times n factorial. So in fact, the n factorials would cancel and I just have n plus 1. We've seen this trick a few times. So now as n gets bigger and bigger and bigger, in fact, yeah, let me go ahead, recall this, why this works out, in case if anyone has forgotten. So n plus 1 factorial is equal to n plus 1 times n minus 1 times all the way down to 3 times 2 times 1. And this right here is the same thing as n factorial. So n plus 1 factorial is the same thing as n plus 1 times n factorial. So that's why these things cancel out. The n factorials would cancel, and we just have the n plus 1s. Okay, back to what I was saying about this limit, right? We can go ahead and factor out this absolute value of x because it's constant with respect to n. There's no n's in it. And now the limit as n goes to infinity of n plus 1, well, the absolute value of n plus 1, which is the same thing, is infinity. And when can I have this less than 1? And the claim is, well, you can't, right? So in this case, according to our convention, as above, we said that the radius of convergence is 0. So the only point where this actually converges is when x equals 0, because then it would just be adding a bunch of zeros to it. Otherwise, this n factorial makes this way too large, as it turns out. So when x equals 0, it works. Otherwise, it doesn't. So the interval of convergence is actually just a single point. So we use these braces, 0. So if x equals 0, it converges. Otherwise, no hope. So this is one of these cases, right? We said that sometimes it'll always converge and the radius will be infinity. Sometimes it won't converge, the radius will be 0, except for maybe a single point. And then sometimes there's a nice radius of convergence. All right, I think I have just one more example for you here. Again, we want to find the interval of convergence. This one's less interested in the radius of convergence. We'll probably find it anyway. But the interval of convergence for this power series, and again, we're going to start with the ratio test. Start with the ratio test to get us our open interval of convergence. So again, we see some good cancellation here. And so we're looking at the limit as n goes to infinity of the absolute value of, it looks like I have 1, negative 1, and it looks like I have a 3x plus 5. And so this is going to be the same thing, well, there are no n's, right? So as n goes to infinity, well, there are no n's. So this is just 3x plus 5, the absolute value of this, is less than 1. And so I want to remind us of some algebra trick here. So in this case, the claim is that I want to go ahead and factor out a 3 from this left-hand side, right? So let me motivate this. Go up here, we're trying to make this x minus a. The absolute value is less than r. So I need to get x by itself. But my x has a 3 by it. So I need to somehow get rid of this 3. So this is why I need to do some extra algebraic steps. So I'm going to factor out my 3. And when I do this, I get x plus 5/3. And then, well, the absolute value of 3 is just 3, so I can factor this out of the absolute value in some sense. And then finally, I could go ahead and divide both sides by 3. I wouldn't need to flip the inequality because I'm dividing by a positive number. And now we can see we have this setup, right? We can see, first of all, we have it as this x minus a, the absolute value, is less than some r. So this is telling me, first of all, that a is negative 5/3 and that r is 1/3. So if you're wondering what is the radius of convergence, it's 1/3. In our case, we weren't so interested, right? We're just looking for the interval of convergence, but this is some good algebraic trick here that you may need to know for your homework, quizzes, exams, stuff like that. So, okay, let's go ahead and find the interval of convergence. So the interval, we're going to go ahead and break this up using our theorem into a nice compound inequality. And then we're going to go ahead and subtract 5/3 from both sides. So to subtract 5/3 from the right, it's negative 4/3. And when we subtract 5/3 from the left, it's negative 2, or negative 6/3. So the open interval of convergence is from negative 2 to negative 4/3. Okay. So I may be highlighting this a little preemptively. We need to figure out the endpoints, right? So this is just asking for the interval of convergence, not the open interval. So I need to test the endpoints. So let me add a little box over here. So my first endpoint is x equals negative 2. What happens if I plug in x equals negative 2 in for x? So I have my negative 1 to the n times, so negative 2 times 3 would be negative 6. Negative 6 plus 5 is negative 1 to the n. So in this case, this would just be the sum of 1 from n equals 1 to infinity. So the limit of our sequence, right, it's just 1, Well, it's 1. So this is going to diverge by the nth term test, right? The limit of our sequence of terms is supposed to head towards 0, but this one's just 1. Okay, so it diverges at -2. What about at -4/3? If I plug in -4/3, well, -4/3 times 3 would be -4 plus 5, that would be +1. So to have -1 to the n times 1 to the n, well, this is going to be the sum of -1 to the n. So I'm going to be adding, a +1, then a -1, then a +1, and a -1, and this is going to diverge. Again, by the nth term test, because the sequence here, this -1, does not converge to anything. It goes back and forth between positive and -1. And if we want the series to converge, we need the sequence of terms to approach 0. So in this case, we don't add in either endpoint, and this is our final answer. This is the interval of convergence. All right, and with that, I think we're just about set with 11.8, all ready to do our homework. I'll see you next time in 11.9.